Okay. Yeah, let's just get started. So, okay, so today we'll go more into, Riemann integrals. So, okay. So before that, let me just say quiz 9. I don't know why, but the answer on question 3 should be 0. Yeah, I don't know why they marked the first one as an answer too, but it should be 0 because the sixth derivative of a degree 5 polynomial is 0. Okay, so I just gave everyone full credit on that. Okay, so let's get started. So let me recall a monotonic function is on an interval is basically it's either increasing or decreasing. So this does not, it's one or the other, yeah. So it's not both. So, an increasing function or decreasing function. And then a theorem says that every monotonic function on AB, function f on AB is integrable, right? Because you don't really want to, unless they say check is integrable, right? By definition, you don't want to use that upper lower sum every single time, right? So, and then same for continuous functions. Okay, so these are common facts now, right? If FG are integrable on AB, and if f is smaller than g for every x, for all x in AB, then the integral is smaller, yeah? So hopefully this is clear, right? Because if f is always below g, the area under the curve of f is smaller than area under the curve of g. And if g is continuous, non-negative function on AB, and if integral a to b g of g is 0, then g is identically 0. And identically 0. So note continuity is important here, right? Because you could possibly just keep, let me think. So like something like this, right? So something where maybe on 1, 2, it's like it hits value 1 at 3 points, and then it's like 0 otherwise, right? The integral here is 0, but g is not identically 0, right? Because it takes the value 1 at like 3 points. But the at 3 points it shouldn't affect your integral, right? I mean, a point has like no area, right? Because you have height, but you have no width, right? The width is like 0. So when you do your rectangles, it doesn't really account for anything. So you see here, continuity is important because what does continuity give, right? Continuity says like if you're not 0 at a point, you can't suddenly just dip down to 0, right? Like here, every point afterward is 0, right? Continuity says, if you're not 0 somewhere, then on some interval, I don't care how you look, but it can't be 0, right? And once you're not 0 on an interval, well, that interval has, has positive area, right? Because length times width is now strictly positive, and then that'll contradict the equal 0 part. So continuity is very important here. Okay. And then this is also a common thing. It's the same for sums, right? So if f integrable on AB, then absolute value of f is integrable on AB. And not only that, we have this, yeah. So no, a priori, I could not write the right-hand side without the statement, yeah. So I needed that absolute value of f was integrable to write the right-hand side. Okay, so hopefully these are all pretty clear, yeah. And then here is also basically a priori, this is not obvious, but hopefully, you know, I don't think it's that hard, but f integrable on AC and AB as CB, then f integrable on AB and integral A to B, f is integral A to C, f plus integral C to BF. Yeah, so I mean, picture-wise, it's just this. So, so here's A, here's C, here's B. Area under the curve from here to here plus area under the curve from here to here is area under the curve of the whole thing. So why is this a priori not that obvious, right? So let me ask this: which one is it easy to prove that, you know, this way or this way? Let me ask that. Or maybe let me change the question. Why is it not so obvious? So if you wanted to prove this, you would have to take a partition of AB. Now a partition, right, of AC, like partition of AC, right? The start point is A and end point is C, right? That's what partition is. And then I don't care how many points are in between. But what you're gonna notice is any partition of AC plus any partition of CB, right? You know, the start point is C. Sorry, start point is C, and then the end point is B, right? This gives a partition of AB, right? So certainly, you know, like the sum of two partitions gives me a partition of the whole thing. But a partition of the whole thing need not be a partition of the two, right? Because why? Because you don't need to have you see, if you add them, you always have the point C, right? So, you know, a partition need not have the point C, right? I could choose some other value in between. So, but like, so not all partitions of AB can be split to sum of partitions, right? So partition of AC, right? What I mean by this is partition of AC plus partition of AB, right? Of course, the idea of the argument is you could choose, you know, points close to it, right? But that's why it's not a priori obvious, because not every partition of AB can be split into a sum. Okay. Any questions so far? Okay. So definition. This is just, you know, f on AB piecewise. You know, I'm just going to define a piecewise function, piecewise monotonic, if there exists partition P equals A is T naught less than T1 less than Tn is B of AB. It's exactly what you think. So F monotonic on every interval. So what it means is, you know, because here we only showed that, you know, it was increasing or decreasing functions were integrable. So now we say, okay, maybe you're increasing on an interval, decreasing on another interval, and maybe increasing on the next interval. So basically, we want to say these functions are still integrable. So, but no, it's only for finitely many. So similar definition for piecewise continuous. I mean, if you like, just think of it like a piecewise function where each function is continuous. That's the long story short. Theorem, F piecewise continuous or bounded piecewise monotonic function on AB, then F is integrable on. So again, we really want to start using this because, I mean, unless the question on the final is exactly like prove this, right? I mean, you don't want to keep using that upper, lower something, right? Just takes way too much effort than just quoting something, right? So okay. This is not, I don't think this is that important, but I'll just write it. IVT for integrals. F continuous on AB. Then there exists X in AB such that F of X is 1 over B minus A integral AB of F. Okay, so let's get to the important stuff now. So there was that question, right? When can we pull limits in? If I have a sequence of functions, when is this, you know, equal to AB limit n goes to infinity fn of x dx, right? Assuming this limit exists, yeah. So we have two big. So in the past, what did we say? Who remembers? So when can we pull limits in? So it was that section where I said like you can swap. There's no sum right now. Uriel. Not uniform continuous, but uniform something else. So I mean, yeah, uniform convergence, right? If the thing converges uniformly. So it turns out that this is just a special case of one of the two big theorems. So there's two big theorems. And do you all remember? I think it was on a quiz in the beginning. I asked you to show if something converges uniformly and the functions bounded. Then like the functions are like uniformly bounded, right? If you converge uniformly on like AB, then like you're pretty much uniformly bounded. Do you all remember that? It was like a quiz problem. Like I forgot what it was. It was like Fn converge uniformly to F. Show F is like shows the Fn's are like uniformly bounded or something like that. like fn's were bounded by like mn's, and then I said show it's less than or equal to like 1 capital M. Hopefully you all remember that. It was like, I'm pretty sure it was on a quiz or something. So the special case is DCT. So dominated convergence theorem. Most people do write DCT. It's a common notation, so you should write that too. So it says Fn integrable on AB, and Fn goes to F pointwise. F integrable. Then if there exists M such that, so actually it's an assumption. So there exists M such that Fn of X is less than or equal to M. Right, so this thing, yeah, sorry, maybe it might have been 140A that I asked this, but for all N and for all X, then limit N goes to infinity, AB Fn of X dx is AB. If you bring the limit in, since the limit converges to F, it's F of X dx. Right? So yeah, so uniform convergence will give this, because uniform convergence will give you this bound. So, okay. Any questions so far? So uniform convergence is like a special case of DCT, pretty much. Okay, so now there's MCT. So monotone convergence theorem. So Fn integrable on AB, and F1 of X less than or equal to F2 of X less than or equal to blah, blah, blah. For all X in AB, and Fn goes to F pointwise. So in this case, it's exactly what it sounds like monotone. I just defined monotonic functions in the beginning. So I mean, in this case, it's increasing, right? So F integrable on AB, then the limit is, you could bring it in. Okay, so big question someone might ask, and I don't think the book goes over this, but what if your function is decreasing? So this is a common question students ask. What? Because it says monotone, right? Monotone need not be increasing. It could be decreasing. So it's a famous proof. So I mean, let me just go over. So what if, what if instead we have this? So on and so forth, right? Then what do you do? Basically, it's reduced to the increasing case. So here you're gonna need something. So yeah, as long as F1 is like integrable, then you're good. So consider function g of x equals F1 of x minus Fn of x. What can you tell me about this function now? Anyone? Is g of, oh, sorry, that makes no sense. Gn of x, sorry. Gn of x is F1 of x minus Fn of x. What do you know? Is this function increasing or decreasing? If we're assuming, that. So if we assume this, right, is Gn of x, is it increasing, decreasing? What is it? Anyone? So let's look at the first few terms. What's f when n is 1, it's 0. When n is 2, it's f1 minus f2. When n is 3, it's f1 minus f3. But knowing the thing in the blue line, what is it? I'm telling you it's monotone, but you have to take it. Is it increasing or decreasing? So, no one. So it's no, right? Because here, right? Since let's just think about it. Minus f2 of x. The next term is f1 of x minus f3 of x. Which one's bigger? You're gonna get this, right? Because f3 was smaller than f2, right? So when I subtract something smaller, I get something bigger, right? Like just think like, I don't know. If you like 5, 3, and then the next term's 2, right? 5 minus 3 is less than or equal to 5 minus 2, right? So hopefully that's clear. So is everyone clear that gn is actually increasing? So gn of x is, first off, it's integrable because difference is a difference of integrable functions, and it's increasing, right? So we have g1 of x less than or equal to g2 of x. So on and so forth. And gn of x goes to what? It goes to f1 of x minus f of x pointwise, right? The reason for this is because fn goes to f pointwise. Now we're in the case of MCT, right? I changed from this way to this way by considering the difference. So by MCT, limit n goes to infinity, abgn of x dx is integral ab f1 of x minus f of x, right? But what was gn, right? Gn was f1 minus fn. So this is limit n goes to infinity, integral ab f1 of x dx. So I'll split it up, minus limit n goes to infinity, fn of x dx, right? But and then this thing is, I'll split it up too. It's plus integral ab f of x dx. But these cancel, right? Because this thing doesn't even, this thing has no n in it, right? So this limit is just the thing itself. So these two will cancel, and then you'll get the result. Yeah, you need. So did I mess something? Yeah, there should be a negative sign here. Minus. So you get, if you divide by the minus sign, you get. Yeah, so monotone, the MCT, basically you just need one way, because for the other way, you prove it like this. So that's why the book only shows like one way. But it is true for the other way, if the arrows go the other way. Okay, any questions so far? So, great, okay. So, let's go to the questions now. So 33.4. Okay, so 32.4. Give an example of f that is integrable and absolute value of f is not integrable, and absolute value of f is integrable. So give example of f not integrable on 0, 1, but absolute value of f is. So again, remember that theorem I just wrote somewhere? This thing, right? If f is integrable, then absolute value of f is, right? So, but it need not be the case that, like, absolute value of f is integrable and then the converse is not true, right? So we're pretty much saying, we're proving the converse is not true. So, so here, obviously we need something negative, right? So the thing that comes to mind is, remember we sort of showed last time. Let me just put, instead of f, like something like 0 for x in q, and then like 1 for x not in q, something like that. This was not integrable, right? So obviously this will not work, because if I took h to be f, I mean, everything's positive, right? Absolute value of f is still f. So we need to change this somehow. So what's the easiest way to do this? Well, define f to be, instead of 0, make it like -1. And this is not integrable, right? Can anyone tell me why? So let's go over that later. But absolute value of f, of x. So let me just write of x. This is just the one. This is just the function 1, right? And I mean, you could show constant functions are integrable. So why is this one not integrable? Because again, the lower sum is what? Given any p. 0 equals t1. I think they start at t1. Actually, let me check something. Does the book start at t1 or t0? Oh, they start at t0. So t0 less than t1, and then less than t2, all the way to less than tk, right? I mean, I don't care what the partition is, because what is the infimum here? tk minus 1. What is the infimum on any interval? Anyone? So for the lower sum, I need to take the infimum of my function, right? So what is the infimum? Yeah. So this is just -1. Let's pull the negative out. And this sum is just a telescoping. Oh, why did I put infinity? Sorry. This should go up to and let me change this to tn. Yeah, so up to n. So what is this? This is just b minus a, right? Because if you like this thing here, t1 minus t0 plus t2 minus t1 plus t3 minus t2, you'll see like every term other than the first one and the last one survive, right? And sorry, not b minus a, 1 minus 0. Yeah. Because my b is 1 and my a is 0. So here I get is -1, right? And then similarly, my upper sum. So this holds for all partitions, right? So holds for all partitions. For all partitions P, right? So L of F is just -1. But U of PF is the same thing, right? Given any partition, it's the soup is just 1, right? So this is similarly, you're gonna get 1 times 1 minus 0, which is 1. So again, so you get u of f is 1. So they're not equal, so it's not integrable. Okay, any questions so far? Okay, so let me just maybe go over a homework question because I think it's kind of a bit hard. So do you all remember that function I gave you the last time? Let me see if I can find it. Right here, I am x for a rational x and 0 for irrational x. So for x and q, 0 for the lower sum is 0, so L of f is 0. The hard part is finding u of f. Was anyone able to do this? So this is actually a bit difficult. Did anyone do that on their homework? Because you can show it's yeah, but so what you end up doing is basically, let me just write something like this. If you take the partition given by 0, 1 over all the way to bn over n, then obviously you can check that the soup is the endpoint, the bigger point on the interval. So we get that here. It's like I equals like 1 to, I'd say, how many terms are there? Bn, right? Of I over n on the interval I. So let me just write this. So I over n minus I minus 1 over n, right? And then soup of f on this interval, right? So this will give you, I think, what you said, right? 1/2 b squared, I'm assuming. So not exactly, but the soup is I over n. And then this is 1 over n. So you have 1 over n squared sum I equals 1 to bn of I. And this is just 1 over n squared times bn times bn plus 1 over 2, right? And basically when n goes to infinity, this goes to b squared over 2, right? So that should be what you got, right? Yeah. But the hard part is, so I found a sequence of partitions going to this number. What does that mean? Obviously, not all partitions are given by this, right? So that only means that this is true, right? So the hard part is how do you get equal? So did anyone show that, or right? Because if you think about it, the u of f is the infimum over all partitions, right? Your partitions here only have rational points in it. Like there are many partitions where the points are like irrational, right? So so what do we do? Well, basically what you do is, this is exactly given any partition, what you're going to notice is we're just calculating the integral of x. So let's change the question. Let's calculate g of x equals x, and let's calculate u of g and L of g. Obviously, this is b squared over 2, but let's just do it. So u of g is the exact same thing, right? Because basically take partition 0, 1 over n, 2 over n, all the way to bn over n. So what do we get? It's the exact same thing, right? Because I get I equals 1 to bn of I over n times 1 over n. And what did we calculate that as? That is 1 over n squared bn plus 1 over 2. And this goes to b squared over 2, right? Obviously, we know the integral of x is x, right? But I'm just proving it directly. So I know similarly u of g, sorry, is less than or equal to b squared over 2. And then the lower sum is the same thing, right? The lower sum, I take the smaller one, right? So I take the I minus 1 over n integral. And this will give sum equals 1 to bn I minus 1 over n squared. And this, I'm sort of shifting by 1. So if you like, just to make this simpler, yeah, you should get something similar, like instead of bn, I'm guessing it's going to be like bn. Since I subtract 1, it's going to be something like this. You should check this, but it's something like that. But basically, b times n. But basically, this thing goes to b squared over 2 as well. So I know L of f is bigger than or equal to b squared over 2. So in particular, L of g. So I know that, u of g is L of g, which is b squared over 2, right? We should expect this because that's integral of x. But what you're going to notice is for any partition P of 0b, u of pf is just u of pg, right? I mean, we sort of saw it here. we get the exact same thing, right? And it doesn't matter about the partition, because no matter what point I choose, it's always going to be the value x, right, for the soup, the value x at the endpoint, and same for the function x, right? But that means that infimum over all partitions u of pf is equal to infimum over all partitions u of pg. But we know this thing is integrable. It's, this is just b squared over 2. So this has to be b squared over 2. Is everyone clear on this? I know I went off. Hopefully you see why I proved the other question. Yeah. Because your upper sum pretty much behaves like the function x. In fact, the upper sum is exactly the same. I don't know what 8D is. So what is 8D? I don't have the prom in front of me, but can you just tell me what it's about? Or
Oh, I think that was the one we went in office hours. Maybe.
oh, is it exactly that one, or?
Yeah.
Oh, okay. So can you remind me what it was? So I think it was. Can you remind me the
Uh,
formula for an, I
oh
guess?
yeah. It was wait.
Like the sum. Uh,
Yeah. The first like A0 is 1, A1 is alpha.
no, like the summation formula. What is it?
Wait, you wrote AN equals sum of it's a product. Like AN is
Oh,
alpha.
sorry. I meant like, is it like something over n factorial? I forgot. Like
Oh yeah, it's alpha times alpha minus 1 all the way to alpha minus m plus 1.
minus.
Uh yeah, and yeah, divided by n factorial.
Okay. Okay. Great. So is that the thing you want me to go over? Like I forgot what it was. I think it was NaN plus n plus one, an plus one is what was it? Alpha an. Is that what you want me to go over, or anyone? Yes. No. Uh. Uh. Xiao Han and Shun Sheng. Is that what you wanted me to do? So. Okay. Great. Okay. Yeah. So this one is just a brute force calculation. So let's see. So if I multiply by n, I get uh, n alpha minus one alpha. So I'm gonna work from here. Yeah. So alpha minus n plus one. So this is n times an, and then I'm adding n plus one. So n plus one will cancel the n factorial. Yeah. So this is alpha minus 1 all the way to, so since it's n plus 1, this is alpha minus n plus 1 plus 1 over n factorial. So is everyone clear so far? So this n plus 1 canceled with the n plus 1 factorial on the bottom. So I get n factorial. Is everyone good so far? I skipped like some algebra steps, but okay. Now this thing, let's sort of write it out. Alpha minus 1 alpha minus n plus 1 over n factorial plus, so what is this? So if I alpha minus n, right, it goes up to alpha minus n. Yeah, so from here, let me ask you, which term is, I can factor out an alpha, this thing on top, let me just write, this thing here is contained in here, yeah, because this thing goes all the way to alpha minus n plus 1, and the right hand side, the right term, I mean, goes all the way to alpha minus n plus 1 and one more, right? Because if you think about how factorial works, so what I'm going to do is I'm going to pull out alpha minus 1 all the way to alpha minus n plus 1. Yeah, so on my first term and my n factorial. So what's left? So I pulled out this one. I pulled out this whole thing and this thing. So what's left is n alpha. And what else? So I pulled out everything but alpha minus n, I believe. So whoa, not n alpha. Sorry. I pulled out everything here. I don't know why I didn't box the alpha, but this should be n, right? Because I only have n left. And then here I have alpha minus n. So I just have alpha. So this thing's just alpha, but this thing is exactly an. Yeah. So I get it's alpha an. And that's this part, right? So we are done. Is everyone clear on this? It's just algebra. So everyone clear so far? Yes, no. Okay. What was the second part? Leonard.
It was to show that the
Like I think it
1
was like
plus
1 plus.
x, yeah, and times the derivative is the same, equal to alpha times g of x.
Yeah. Okay.
Yeah.
Okay. So and I guess the end is they both satisfy this differential equation, so they're equal. Okay. So here, what was g? I forgot where the sum is. Start n equals 0 to infinity an x to the n, right? Is that what it was? Or
Yeah.
okay. This is also calculation, so let's do it. So 1 plus x. And g prime is, well, what's derivative, right? Inside radius, so inside absolute value of x less than 1, right? We can differentiate term by term because that's the radius of convergence. And this is n an x to the n minus 1. But we start at 1, right? Because we lost a term. We lost a constant term, right? So we start at 1. Now, this is alpha times whatever this is, right? Okay, so I need to show this, so let's work on this side. Yeah, let's work on the blue side. So what do I have? Let's FOIL. So I get sum n equals 1 to infinity n x to the n minus 1 plus sum n equals 1 to infinity n x to the n. Yeah? Everyone good so far? So everything here starts at 0. So I need to make these sums start at 0. So let's reindex. So here, let's start at 0. But when I do that, I have to, if I subtract 1, I have to add 1, right? So is everyone clear that these series are equal? So if I plug in 1, if you plug in 1, I get 1 times a1 x to the 0, right? So if I plug in 0, I get 1 times a1 x to the 0. So it's the same series, right? Reality check. And then the second one, well, I could just add in 0, yeah? Does everyone understand why? Because what's the n equals 0 term? 0 times a0 times x to the 0 is 0. Yeah, so it doesn't hurt to just start at 0 because at 0, it's 0. I didn't change anything. But now we can add it, right? So this thing is sum n equals 0 to infinity n plus 1 an plus 1 plus nan. And then we have a factor of x to the n. Okay, what is this? We calculated it 3 minutes ago. This thing was alpha an, right? And then we're done. So this thing is alpha g of x. Okay, is everyone good so far? I mean, that's about it. So everyone understand? Okay, great. I guess that'll end it for today. Yeah. So yeah. Make sure you do the quiz. It's on, it's just calculate upper Darboux integral, lower Darboux integral. So